Let's now consider some more consequences of Gauss's law pertaining to conductors. So we start with this solid conductor. And we're going to carve out a cavity inside of it. Sounds like fun. So boring out this hole inside and put a Gaussian surface around it. To keep in mind that this is a two-dimensional slice of a three-dimensional extended object. So this Gaussian surface really encloses a volume that includes this cavity. Now the net charge in the cavity must be 0. Why? You can't have any charge enclosed because the E field is 0 everywhere on this Gaussian surface. So that's the requirement. The E field has to be 0 here. If there was charge enclosed, then there would be an E field at the Gaussian surface, which would cause the charges to move till the E field went away. And that's the condition that always must be met. So we have to believe that and rigorously stay committed to it. Now we're going to do a little experiment. We're going to put a charge plus Q inside that cavity. So there's the cavity, Gaussian surface. We're going to put a positive Q inside of it. Think of it hovering without touching anything right now. So there it is. Well, it seems to me then that we are enclosing a charge. So there is an electric field, isn't there? Well, no, the electric field has to be 0 for the same reasons. But it's not very obvious that this would have no charge enclosed or a 0 electric field, because it looks to me like there is a charge enclosed. Well, again, the condition of the E field being 0 is true. So the Gaussian surface indeed must enclose no net charge. There is a solution to this dilemma, and we're not quite done with it. In fact, when we put that little plus Q in there, it's going to change the conditions in the rest of the charged conductor. So the solution is that we have to move charges around until the condition is met. So negative Q has to be drawn from the outer edge and put on the inside of the inner cavity. So it looks like this. There they are. Now, if this collectively is negative Q, then we don't have any charge enclosed now. Well, that's good. So that's what happens. So right now the total charge enclosed is 0. But what happened to the surface charge density? Okay, this thing had a charge density based on these positives. But we just drew negatives to the inside surface of this, and they came from the outer edge. If you draw a negative from the edge, what happens to the edge? Well, it really means some electron got taken from an atom, so it's more positive now. So we increase the surface charge density of the outer edge, and look at how this goes. There they are. We have an increased surface charge density as the edge is more positive. And in fact, the way that this charged conductor looks to the outside world is that it produces an E field that's certainly not 0, because there is a surface charge density resulting in an E field. And actually there's really no way by looking at this E field to know just what in the heck is going on inside here. But it really doesn't matter. These things actually did have to take place in this situation. Now let's mess around with this thing a little more, and let's allow the charge Q to touch the inner surface of the conducting volume. So there we go. We lower it down, and charge Q, the object itself, you can think of that as a little conducting sphere with charge Q on it, but very small in size. Well, it doesn't really matter even what the size is. It's now a little tiny ball of charge Q. And when that charge touches the cavity wall, it becomes part of the overall conductor. All right? And therefore, the charge must leave and go to the outside surface. Because we could, in a magnified view, we can see this, we could construct a Gaussian surface that includes the region of the conductor and the charge here. So let me do that. We can't enclose any charge by this Gaussian surface, So here's the Gaussian surface I'm going to draw. You notice this Gaussian surface is everywhere inside conducting material. And so the Gaussian surface cannot enclose any charge. The only way for that to happen is for the charge to have left this little sphere. So if we bring the sphere inside and touch the inner surface, whoop, the charge shoots to the outer edge, and there is no charge contained anywhere inside here. So that's kind of neat. And that's actually something that I can demonstrate for you as well. So here's another visualization of a brief sequence of what we just covered. We have a hollow metal sphere that's not charged. Well, this actually, it wouldn't matter if it was charged or not. It doesn't really matter. But right now, I'll say it's not charged. Now we're going to place, we'll put a negative charge inside that cavity. Now, ignoring this hole, which modifies things just a little bit, but we've essentially put a charge inside a hollow sphere. This is a slice of a hollow sphere. Well, this is going to induce a charge separation in the material. So the negatives are going to draw positives to the inside of this, which is going to put negatives on the outside here. So there's the positives and there's the negatives. The outside surface of that initially uncharged hollow sphere is now charged as a result of this charge inducing that charge separation. And then if we let it go ahead and clunk down on the bottom, we actually let it touch, the charge bleeds out of this into here. And so we've actually permanently charged the hollow metal sphere. And all of the charge has now zipped out to the outer edge of the hollow metal sphere. So any Gaussian surface we would draw is not going to enclose any charge. In other words, you don't have any permanent charge on the inside surface. You only had charge on the inside surface of this sphere while there was that induced charge separation before this object made contact. And that can happen because you could conceivably put a Gaussian surface around here such that you enclose no charge with these positives. But over here, it must all drain away because this is now part of the conducting surface. All right. So I will demonstrate this for you, and when we do so, we can see that when we pull this charge back out and do a test on it, the charge has indeed been removed. So there is no charge left. It really did get pulled away. An quantitative example of this exact thing then would be, well, let's say that we have charge of 3 nanocoulombs in a conductor. In this case, then every nanocoulomb is represented by a plus. So we're going to go ahead and produce a cavity and put in a negative 5 nanocoulomb charge inside the cavity. All right, so in the next scene, what does that do? Well, that negative 5 nanocoulombs, if it's hovering there, we put a Gaussian surface around here. We better not enclose any charge. So we better have plus 5 nanocoulombs on the very inside surface of the cavity. That's exactly what happens. There's positive 5 nanocoulombs. Now any Gaussian surface will not enclose any charge. The net charge of the entire object, however, is going to manifest what the whole charge is. The actual charges. We had plus 3 and we have minus 5. Sounds to me like that's minus 2. It's going to show up on the surface, and it is minus 2 nanocoulombs. So there they are. So from an outside perspective, minus 2 nanocoulombs. There's an electric field that goes in to this entire system. And again, you have no knowledge of the details of what's going on inside here by just looking at the outer surface. For all you know, somebody had an initially uncharged, solid, conducting object and put negative 2 nanocoulombs of charge on it. Same difference.